In the silent, frozen expanse of space, a million miles from home, a golden eye unfolds, a creation of staggering ambition. It is a Sentinel, a time machine, humanity's most audacious attempt to witness the universe's own birth, to gaze upon the first dawn. This is the James Webb Space Telescope, a $10 billion dream made manifest in gold-plated beryllium wire and hope. Its singular purpose is to collect the faintest, most ancient light photons that have journeyed for over 13 billion years, carrying within them the ghost of a beginning. The first images arrived, and they were everything we had imagined and more. They were jewels scattered on black velvet nebulae like celestial paintings, galaxies colliding in a silent gravitational ballet. Yet even in this perfection, a subtle spectre lingered. A whisper in the data, an almost imperceptible flaw. It was not a failure, not a mistake in the mirror's curve, but a fundamental truth of light itself. A cosmic haze, a luminous penumbra surrounding every point of brilliance, threatening to shroud the very secrets the observatory was built to uncover. The faintest, most distant island universes, the nascent seeds of creation, remained just beyond our grasp, lost in a shimmering veil. The engineers knew of this challenge, this optical artifact. They had accounted for it, modeled it, deemed it an acceptable limitation of even this near-perfect instrument. The universe, it seemed, would hold back its oldest secrets, guarding them behind a curtain of its own physics. What no one anticipated was that the key to parting this veil would not be found in a sterile NASA cleanroom or an advanced optics laboratory. It would emerge from a world of algorithms and code in the minds of a small group of students on the other side of the planet, who saw not an insurmountable barrier, but a puzzle waiting for a solution. They were about to teach humanity's great eye a new way to see. To comprehend the scale of this achievement, we must first journey back not just decades, but centuries, to the very dawn of cosmic curiosity. Imagine Galileo Galilei in the year 1610 turning his crude spyglass away from the ships in the Venetian harbour and toward the heavens. In that moment, the universe expanded 1,000,000-fold. He saw craters on the moon, witnessed moons orbiting Jupiter, and resolved the hazy band of the Milky Way into a countless multitude of stars. Each new telescope since has been an extension of that revolutionary gesture. From the giant reflectors of William Herschel, which mapped our galactic home, to the great leviathans of Mount Wilson and Palomar, which revealed that the faint spiral nebulae were in fact entire universes, each instrument peeled back another layer of the cosmic onion. Yet all of them, from Galileo's humble lens to the largest terrestrial giants, shared a common enemy: the Earth's own atmosphere. Our planet's shimmering, turbulent blanket of air, the very thing that gives us life, blurs, distorts, and blocks the delicate light from distant worlds. For generations, astronomers dreamed of placing an observatory above it all in the pristine, silent vacuum of space. That dream was realized with the Hubble Space Telescope. Launched in 1990, it was a marvel promising to revolutionize our understanding of the cosmos. But its initial days were marked by a crushing public disappointment. The images were fuzzy, unfocused, a microscopic flaw in its primary mirror. A mistake the width of a human hair had created a devastating optical error called spherical aberration. The dream seemed broken. The story of Hubble's redemption is now legendary, a testament to human ingenuity in the face of near-catastrophic failure. Astronauts on a daring shuttle mission installed corrective optics, a set of contact lenses that fixed the telescope's vision. Suddenly, the universe snapped into breathtaking focus. Hubble became the most productive scientific instrument ever built, its iconic images transforming our cultural perception of space. It measured the expansion rate of the universe, found supermassive black holes, and gave us the deep field's portraits of thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length. But Hubble saw invisible and ultraviolet light. It could only look back so far. The light from the very first galaxies born in the cosmic dawn has been traveling for so long that the expansion of space itself has stretched its wavelengths, red-shifting it deep into the infrared spectrum. This ancient light is invisible to Hubble, and it is blocked by our atmosphere. To see it, to witness the moment the universe first switched on the lights, we needed a new kind of eye, an infrared eye, a much larger, much colder, and much more complex Sentinel. This was the genesis of the James Webb Space Telescope. Its creation was a saga spanning more than 2 decades, a monumental effort involving thousands of scientists and engineers from across the globe. Its primary mirror, a breathtaking mosaic of 18 gold-coated hexagonal segments, was over 6 times larger than Hubble's design to collect the faintest whispers of light. It was so enormous it had to be folded like origami to fit inside its launch rocket. To see in the infrared, the observatory itself had to be unimaginably cold, as its own heat would blind it. So a 5-layered tennis court-sized sunshield was engineered, a magnificent gossamer parasol designed to block the light and heat from the sun, earth and moon, keeping the instruments near absolute zero. This entire delicate marvel then had to travel 1 million miles away to a gravitationally stable point in space known as L2, where it could maintain its perfect frigid vigil. The deployment sequence alone, involving hundreds of single points of failure, was the most complex series of robotic maneuvers ever attempted. It was a gamble of epic proportions, and it worked flawlessly. The Webb Observatory settled into its orbit, cooled to its operating temperature, and aligned its 18 mirror segments into a single perfect surface. When the first deep field images were released, humanity gasped collectively. We saw gravitational lenses warping space-time stellar nurseries of exquisite detail, and a field of galaxies deeper and older than any seen before. It was a triumph beyond all expectation, and yet the ghost remained. This subtle, pervasive diffusion of light. To understand its nature, we must step away from the cosmos for a moment and consider something more terrestrial. Picture a solitary lighthouse on a foggy night, its powerful beam cutting through the mist. The light source itself is a tiny point, the filament of a bulb. But as its light travels through the fog, the water droplets scatter the photons. The crisp, sharp beam becomes a soft, luminous cone. From a distance you see not a pinpoint but a glowing orb, a halo. The fog has taken the perfect point of light and spread it out. This transformation is known as the point spread function, or PSF. It is the unique signature of how any imaging system, be it a human eye or a telescope, spreads out light from a single point source. No telescope is perfect. The laws of physics themselves decree this. Even in the vacuum of space, light diffracts as it passes the edges of the mirror and the support structures holding the secondary mirror in place. This diffraction creates a characteristic pattern. For the Webb Observatory, with its hexagonal mirrors and 3 support struts, this results in the iconic 6-pointed starburst effect seen around bright stars. This beautiful pattern is in fact an artifact. It's the telescope's PSF. But the diffraction spikes are only the most obvious part of the signature. Far more insidious is the faint, extended halo of scattered light, a delicate haze that surrounds every single object in the field of view. For 99% of astronomical targets, this effect is negligible, lost in the noise. But Webb was built to hunt for that remaining 1%. It was designed specifically to find the faintest, smallest, reddest smudges, the primordial galaxies forming at the edge of observable time. And herein lay the profound challenge. These nascent stellar metropolises, these first cosmic structures, are so unbelievably distant and faint that their entire image can be smaller and dimmer than the luminous halo of a foreground star. A star in our own Milky Way, millions of times closer, could act like that lighthouse in the fog, its scattered light, creating a veil that completely washes out the ancient galaxy hiding behind it. The very tool designed to find these cosmic ghosts was in a way creating its own phantoms that obscured the view. The greatest treasure hunt in scientific history was being hampered by a fog of light, an intrinsic property of the magnificent instrument itself. The astronomical community understood this limitation. They developed complex computational models to try and subtract this glow, but the process was imperfect, laborious, and prone to creating its own errors. It seemed the first chapter of the universe's history would remain partially illegible. The scene now shifts, moving from the cold, hard vacuum of space to the vibrant, sun-drenched campus of the University of Sydney, Australia. Here, in a world far removed from orbital mechanics and cryocoolers, a different kind of revolution was well underway. The revolution of artificial intelligence. A postgraduate student named Yinuo Zhang and his colleagues were not astronomers. Their expertise lay in the burgeoning field of machine learning, teaching computers how to recognize patterns, to learn from data, and to make predictions. They were working on medical imaging training algorithms to sharpen MRI scans or identify subtle anomalies in X-rays. They were experts in seeing through noise, in finding signal in a sea of static. When they looked at the raw data from the Webb telescope, they saw something familiar. They didn't see galaxies and nebulae. They saw pixels and light values. They perceived the subtle halo, the ghost in the data, not as an optical problem, but as a signal processing challenge remarkably similar to their own work. The question that formed in their minds was audacious in its simplicity. Could a neural network be trained to understand the telescope's fog and learn how to digitally remove it? Could they, in essence, teach a machine to perform a kind of cosmic cataract surgery? The concept they pursued is known as deconvolution, the process of reversing the distortion introduced by an imaging system, but their approach was radically new. To grasp what they accomplished, imagine a master art restorer. This restorer has spent a lifetime studying the works of a single old master painter. They know every nuance of the artist's brushwork, their color palette, the way they layered paint to create light and shadow. Now suppose this restorer is given a painting by the master that has been damaged, covered in a fine network of cracks and a layer of accumulated grime. To an untrained eye, the original masterpiece is obscured. But the expert restorer can mentally look through the damage. Their brain, trained on thousands of examples of the artist's pristine work, can intuitively predict what the original brushstroke should look like beneath a crack. They can meticulously clean away the grime, fill in the cracks, and restore the painting to its former glory, because they have learned the fundamental rules of the artist's creation. The Sydney students sought to build a digital version of this art restorer. Their AI, a type of neural network called a vision transformer, would be the apprentice, and the JWST's unique optical signature would be the damage. First, they had to teach it. They couldn't use real before and after pictures from space because no perfect images exist. So they created a massive library of synthetic, idealized space images. These were pristine, computer-generated star fields with perfectly sharp pinpoint stars. This was their collection of undamaged masterpieces. Then they wrote a sophisticated program that simulated the exact physics of the Webb telescope's optics. This program took their perfect images and applied the damage, adding the characteristic six-pointed diffraction spikes and, crucially, the faint extended halo of scattered light. the telescope's unique point spread function. Now they had a vast dataset of before and after pictures. They had the pristine art, and they had the grimy, cracked version. They fed hundreds of thousands of these paired images to their neural network. Over and over, the AI would look at a blurred image and try to guess the perfect original. Each time it guessed it, compared its result to the actual pristine image and adjusted its internal connections, its millions of virtual neurons to get closer the next time. Slowly, painstakingly, like the art restorer learning the master's hand, the algorithm began to understand the signature of Webb's vision. It learned to recognize the precise shape and intensity of the luminous haze. It began to intuit how to defog the image, to computationally gather the scattered light and return it to its source point. The training process took weeks on powerful supercomputers, a silent digital apprenticeship in the art of cosmic restoration. When it was finished, they had created something extraordinary, a specialized intelligence, an expert system whose sole purpose was to see through the Webb telescope's inherent imperfection. They called their creation Self-Supervised Vision Transformer, or SSR-VIT. The digital art restorer was now a master in its own right. The time had come to show it a real damaged masterpiece. With a mixture of trepidation and excitement, they acquired a segment of raw data from one of the Webb Observatory's deep field surveys. This was not a polished press release image. This was the unprocessed scientific data, teeming with information and shrouded in the subtle optical haze they had trained their AI to recognize. They fed the data into their newly trained algorithm. The process was not instantaneous. The machine churned its processors, working furiously, applying the knowledge it had gained from the simulated universe to this genuine dispatch from the cosmos. It was analyzing every pixel, identifying the signature of the point spread function, and meticulously performing its digital restoration. Then the output image appeared on the screen. The difference was staggering. The before picture was magnificent by any standard, a classic Webb image. A field strewn with stars of varying brightness, their six-pointed diffraction spikes emblazoned on the darkness, and countless faint smudges of distant galaxies in the background. But the after picture was something else entirely. It was clean. It was sharp. The halos around the stars were gone, their light seemingly vacuumed up and compressed back into brilliant tight points. The entire image had a newfound clarity, like a veil had been lifted. At first, that was the main impression, a cleaner, crisper view of a familiar scene. But then they started looking closer, blinking between the two images. In the spaces where the luminous fog of foreground stars had been, where the original image showed only a faint, ambiguous glow, objects began to appear. Tiny, faint reddish dots, specks of light emerging from the digitally cleaned background like ships from a fog. They weren't there before, now they were, unmistakably. It was a moment of profound discovery, a quiet eruption in a university computer lab. The students knew what these smudges had to be. These were galaxies. Not just any galaxies, but the very ones the telescope was struggling to see, the ones that had been hiding in plain sight, camouflaged by the light of their cosmic neighbors. But a discovery in science is not a discovery until it is verified. Could these new dots be mere artifacts of the AI process itself? Was the algorithm hallucinating galaxies that weren't really there? This was the crucial test. The team went to work rigorously checking their results. They performed extensive tests on simulated data where they knew precisely what hidden object should exist, and their algorithm found them with incredible fidelity. They compared their findings with data processed using traditional, slower methods and found their AI not only worked hundreds of times faster, but also uncovered faint structures the older methods missed entirely. They prepared their findings, their methods, their code, and their incredible images and submitted them to the unforgiving crucible of peer review. The astronomical community was initially and rightly skeptical. The use of such advanced AI in this context was novel. But the evidence was undeniable. The logic was sound. The results were repeatable. Slowly, skepticism turned into excitement and then into awe. This was not just an incremental improvement. It was a breakthrough. A team of computer science students had developed a tool that could effectively upgrade a $10 billion space observatory, unlocking a new level of its observational power. Their hack was about to open a new window on the dawn of time. Astronomers around the world began applying the new technique to Webb's public data archive, unveiling a hidden universe. In image after image, where once there were a few hundred visible galaxies, the AI-enhanced versions revealed thousands. The cosmos, it turned out, was far more crowded than we had realized. The implications of this discovery are only now beginning to be understood, and they ripple through the very foundations of cosmology. The galaxies uncovered by this AI-assisted vision are not just numerous, they are changing our understanding of how the early universe evolved. Our prevailing models of cosmology suggested a slow, gradual build-up. The first billion years after the Big Bang should have been a time of small, wispy proto-galaxies, slowly coalescing into larger structures. But these newly revealed galaxies are telling a different story. Many of them appear brighter, more massive, and more structured than our theories predicted should be possible so early in cosmic history. It's as if the universe was in a hurry, assembling large, mature stellar cities far faster than anyone had imagined. This presents a beautiful puzzle for theorists. It might mean that the first stars, the so-called population 3 stars, were far more massive and efficient at creating heavy elements than we thought. It could suggest that supermassive black holes formed much earlier, acting as gravitational seeds that accelerated galaxy formation, or it may point to new, undiscovered physics governing the nature of dark matter and its role in sculpting the cosmic web. The student's algorithm didn't just clean up an image, it unearthed a trove of evidence that could rewrite the opening chapter of the cosmic story. We are now faced with the exhilarating task of understanding this busier, more precocious early universe that has been revealed. Beyond the immediate scientific impact, there is a deeper, more philosophical resonance. The story of the Webb telescope is one of monumental hardware, a physical artifact pushed to the absolute limits of human engineering. It is a cathedral of mechanics and optics, a testament to what we can build. But its full potential was unlocked by something entirely different. It was realized by software, by an elegant algorithm, a creation not of physical substance but of pure logic and information. It is a powerful illustration of a new paradigm in scientific discovery. The great breakthroughs of the future may not come just from building bigger machines, but from crafting smarter ways to interpret the data they provide. This fusion of human curiosity, mechanical genius, and artificial intelligence represents a new kind of scientific partnership. It also speaks to the democratization of discovery. The solution to one of Webb's most subtle challenges did not come from the heart of the space agency that built it. It came from the periphery, from a different discipline, from a group of students with a fresh perspective and a powerful new set of tools. They remind us that the universe's secrets are not reserved for a select few. The vast archives of data produced by instruments like Webb are often public, a treasure chest waiting for anyone with a clever idea and the skill to test it. A student in a university lab can now stand on the shoulders of giants and with a few lines of innovative code help them see even further. What does the future hold for this extraordinary new technique? Its application is just beginning. Astronomers are now planning to reprocess the entire Webb Deep Field Archive, a systematic search for the hidden populations of galaxies that will undoubtedly provide the statistical basis for a new generation of cosmic models. The algorithm can be adapted for other telescopes, both in space and on the ground, each with its own unique optical signature, its own particular fog. It can be used to search for the faintest exoplanets, helping to subtract the overwhelming glare of their parent stars. It could reveal faint, extended structures around galaxies, the ghostly tidal streams of ancient collisions and mergers. We have been given a new sense, a new way of perceiving the digital light that our telescopes collect. The journey that began with a curious glance through a simple spyglass has led us to this remarkable moment. We have built a golden eye and placed it at the edge of our world, and it is staring into the abyss of time. It gathers light that is older than our planet, older than our sun, and as we learn to interpret that light with ever greater sophistication, with the help of intelligences of our own creation, the universe continues to surprise us. It is richer, more complex, and more magnificent than our theories had allowed. The faint red smudges revealed by a clever piece of code in Sydney are more than just data points. They are the oldest embers of our own cosmic origins. Each one is a city of 1 billion suns, born when the universe was but a toddler. Within them, the first heavy elements were being forged, the raw materials that would one day lead to planets, to life, to us. By seeing them more clearly, we see our own history more clearly. The map of the known universe has been redrawn, its empty spaces filled in its first moments, brought into sharper, more brilliant focus. And we are reminded once again that our quest for understanding is a perpetual unfolding, a journey not toward a final answer, but into ever deeper and more wondrous mystery. The veil has been lifted and the dawn of everything awaits.